Welcome to Energy System Modeling lecture number 5. And today we'll be going through about the energy storage modeling. So this is a topic that could cover a wide variety of different issues, but I was thinking on talking about just briefly about the energy management strategies, then about the scales, so you understand how much energy is available and how kind of different technologies can be applied for those. So mostly we're talking about large scale energy storages in here. So we're not going to cover too much the household level. The battery energy storages, they can be applied really well to this household level or even this kind of a micro level, but mostly it's going to be on a larger scale. Mathematical modeling of energy storages seems to be said twice in here, so you can see it's an important topic. I'll see if I can remove that from here. It seems that whenever I don't remove or correct something on the spot, it stays in the material. So a little bit about the simulation techniques and energy system sizing, and then hopefully we'll have a little bit more or a little bit time to go through the simulation as a part of an energy system. But that's actually something that we did already kind of before. Just going to check still that did I put the recording on, because that seems to be a problem every now and then. Yeah. Okay, so the energy production or the energy production system. This is the figure that we've been talking about, and in here you don't kind of see the storages. So the storages could be placed on the consumer end of the system or on the conversion side of the system. So they are in that sense really flexible. The conversion side of the system, that's like, let's say, these thermal storages for district heating systems. So those kinds of thermal batteries are being implemented into Finnish district heating systems pretty widely at the moment, and they've been doing that for quite some time already. And now the electricity storages are also kind of ramping up in Finland. And also on the consumer end, you can use especially these small scale battery energy storage systems. They are being offered to the consumers as we speak nowadays. So there's a lot of this kind of a, how to say, leasing, for example. So you get the battery almost for free, but the operator has the ability to kind of utilize your own battery for energy arbitrage. So they can utilize that in their, for example, in the reserve markets. But yeah, the placement of these energy storages, that's rather flexible depending on the type. So the energy management strategies, as you can see in here, if you have the demand and the time of the day, or the time of the year, if you're talking about seasonal storages, there are other kind of types of this energy system or usages for these energy storages. I didn't talk about actually anything in here about, for example, using battery energy storages to improve the quality of electricity, so kind of maintaining the grid stability. So we're talking more about this large scale and a bit longer duration energy storage usages. So peak shaving is something that you don't quite require this energy storages but you can utilize energy storages for that. If I switch off the lights, that can be pretty much peak shaving. So it lowers the demand, but not necessarily shift the energy use to another time. In that sense, you don't need energy storages, but you can utilize it for that. This energy conservation, it just means that you're focusing on improving efficiency. So it doesn't include or it doesn't need to have or involve these energy storages. But you're rather using less energy overall. So energy efficiency is one way of this management strategies. And this load shifting, this is where the batteries and energy storages come into play. So moves energy consumption from high demand periods to low demand periods. And it can be price driven. So in this peak shaving, it doesn't necessarily have to be price driven, grid stability driven, renewables driven, and often requires this energy storage. You can, well, in a sense, for example, a house is an energy storage in itself. It has this thermal inertia. So if you have a district heating peak and your operator can kind of adjust or control your heating system. They might do it in a way that they load up your household or hospital or a bigger apartment building during the night with heat. And then when there's the Monday morning 8 o'clock peak in heat demand because of hot water usage, for example, then they don't have to use the heating for the houses at that point. So the thermal inertia will carry over. So remember these peak shaving and load shifting are the kind of types of energy management strategies that are often talked with the in relation to this energy storages. So a little bit about the scales. If you're talking about this electricity and district heating consumption, so that's how many gigawatt hours per year these cities are utilizing. So these are really rough estimates. They are not nothing but approximate. But district heating 7,000 gigawatts per year and electricity 5,000 gigawatt hours per year. And if you're talking about building types, this kind of an apartment house, so kerrostalo, 0.3 gigawatt hours of heat per year and electricity 0.05. Hospitals, sorry, I had the presentation in Finnish, so it seems to have a little typos in here. So if we're thinking about how much energy is available, for example, in renewable energy at these bursts, because that's kind of like the driving force behind this large-scale energy storages. If you're talking about this point in here, so this is from this year's beginning, January, there was some 150 gigawatt hours produced with wind power at this point. Of course, not all of it could be put to the energy storages, but at least to some extent. In here, you can see the consumption is rather high as well. So not a lot of room to use these energy storages in there. But the amount of wind power in those bursts, you get the idea of how many gigawatt hours do they contain. And Finland's electricity consumption, 8,000, or rather 85,000 gigawatt hours per year, and total energy consumption. So this is just electricity, and the total one is more or less like 4 times higher. So there's thermal energy, and there is the energy used in traffic, for example, and so forth. So those are the kind of scales that we are talking about. Let's hope I'll remember to correct that hospital. And why are we concentrating on these energy storages in relation to this renewable energy, where you can see the energy system bouncing up and down because of this renewable production. So this is a monthly kind of snippet during the summertime in Finland. So wind is going up and down, and then there are these solar spikes. And especially during the summer, since you have the solar spikes, it would be nice to have some better use for those when you have an excess amount of this electricity. And the potential for solar and wind energy. So this is the one that I showed you, I think, in the first lecture. So the area of the circle represents reasonably assured recoverable energy reserves from both finite and renewable resources over the next 30 years. So over the next 30 years, you could cover everything with wind. You could cover everything multiple times over with solar related to our energy demand. Of course, that would require a massive kind of restructuring of our energy system in the global scale. And that would, of course, require a lot of metals and minerals. So the mining industry would have to kind of speed up its actions. And I think I mentioned this one earlier, a really good video, if you have YouTube in there, just type in Mark Mills and energy delusion. So he's a professor from United States, and he's talking about this speed that we are kind of predicting that the renewable energy will propagate. But the thing is, can our mining industry kind of keep up with the pace? So the rare earth elements, and even steel industry, copper industry related to mining, can they keep it up? But the potential is there. So that's why, since these are kind of periodical, intermittent, that's why you need the backup with that. So in Finland, the electricity system is driving itself towards, because of the large installation of wind power, it makes the electricity price really low from time to time, and it's driving itself to a point where a lot of this, because of our market mechanisms, it's driving itself to a point where we don't necessarily have the capacity at every given moment to produce the electricity with these high load hours. If some of the larger power plants, for example, the nuclear power plants, are in maintenance and there's no wind, what are you going to be using? And especially if we're going to have a tax on those sea cables later on, that's going to make our electricity system rather vulnerable. Because we have been fortunate enough to be able to kind of lend Sweden's and Norway's resources for electricity storage, which is related to this pumped hydro. So if we're talking about the technologies nowadays that are at the forefront of this energy storage business, hydrogen is being talked about a lot, but at the moment there is no kind of power to X to power if we're talking about transferring it backwards to electricity. There's one large-ish demo in France, but in the Europe related to gas turbines, but it hasn't been utilized at a large scale, so it's kind of at its infancy. The one that is kind of how to say, it's the largest kind of technology that's been utilized, so that it's at the moment it's winning the game. So pumped hydro, you can see market size of energy storage systems. Pumped hydro is by far the largest. So it's the largest at the moment. It's going to be largest far into the future. But of course, the battery energy storage is are going to take over as well. But you can see that the pumped hydro, so there's a comparison of this energy-specific investment cost and this power-specific investment cost. So in power-specific investment cost, it loses to these battery energy systems, for example, this really short duration flywheel and supercapacitors. But the advantage of pumped hydro is that it has you can store a lot of energy in there because of the systems in Norway and Sweden, for example. They have a lot of this drop height in those systems, and there's a large area to be filled with water. But it can only be utilized in countries that have these rivers or these large ponds, large elevations that can be utilized for that. So not all the countries can use those. So examples on these energy storage technologies. In Finland, they are planning this Ailangan tunturi, they're planning to build a pumped hydro plant, which is going to be 550 megawatts. I don't recall what was, or I don't know even if it was said how much in energy terms that was, but I guess it was a few gigawatt hours that they could store in that. And you can even calculate it by yourself because they are giving. So this is the map from Ailangan tunturi, and that's the blue line in here. It's going to be the kind of tunnel that they can utilize to pass the water through. So surface area about 1 square kilometer, water volume 13 million cubic meters. So you can see the kind of structure of the system in here. So there's the upper reservoir and the lower reservoir, and there's the turbine in between. It's not really exactly that simple, but that's kind of like the principle. A lot of rock excavation has to be done. Water flow rate 300 square meters per second. So the tunnel is going to be with a diameter of 9 meters and 4.5 kilometers long. So it's a massive kind of excavation project, and then you have to build a lot of these power lines as well. So it would be an investment of approximately 800 million euros. And as you have probably seen from a lot of these projects, in some cases, they tend to kind of underestimate this in the beginning. This, in a sense, it's rather proven technology. So the technology readiness level in this technology, it's really high. So it's I would say it's a 9. It's existing technology that's been utilized often. Then another kind of interesting nuance that I wanted to take in here is this gravity battery. Well, in essence, this pumped hydro is gravity battery, but they are planning, for example, in China and I guess in not Sweden, but Switzerland, there was a test of this. And in Finland, in Pyhäsalmi, there's a 530 meter deep this mine. So you lower down a mass in a deep this kind of a mining system, and the capacity was supposed to be from 1 to 10 megawatt hours, so it's not that large. But the advantage of this system is that it has a really good round trip efficiency, and it doesn't the energy doesn't dissipate as a function of time. So you don't lose the energy. In water reservoirs, it can evaporate. In batteries, there's a lot of this self-discharge, but this doesn't self-discharge. You put it on a shelf and it stays in there. This energy vault in Switzerland, 35 megawatt hours. And in China, it looks something like this, approximately 150 meters tall, and it was said to have 12,600 blocks and 25 tons each. So you can understand that it's a massive installation in terms of how much you need to have these solid ground structures for it. So you cannot kind of build it in anywhere or everywhere rather. But in cities, maybe. They still have to solve the problem of what to put in those blocks, because cement actually isn't that good of a material if you're talking about these life cycle costs. So existing structures can be utilized for mines and towers. They require a lot of space and building permit. So the space efficiency, it's like the energy density is 100 times less in this case than in lithium-ion battery. But it's cheaper to some extent, and it doesn't have the energy self-discharge aspect. GAES is one that hasn't, in my opinion, been utilized that to its full potential, because GAES is compressed air energy storage. There are projects underway in China related to, again, utilizing renewable energy sources. So 1,200 million US dollars, 300 megawatts and 1.8 gigawatt hours. So grid balancing and renewable integration in a larger scale. And Canada, so this GAES can be implemented also with this as a water system. So you have to have this watertight underground caverns, and there's this water pressure that's been utilized in there. That's a little smaller project. So energy density again is 100 times lower compared to lithium-ion batteries, highlighting the trade-off between capacity and efficiency in this GAES system. But it's still somewhat promising technology. There's been a couple of these power plants. I think this Macintosh was probably built in the 90s, if I'm not completely wrong. You can check it from Google. And this Huntor was I think in 79. So it's been around. What they are talking about now is making these adiabatic GAES systems. But you can see the scale. It's rather large. So there is 300 and 100 megawatts of electricity. But the round trip efficiency, meaning what you get from the initial amount of electricity, isn't that high compared to pumped hydro. So whenever you have the possibility of using pumped hydro, or maybe in the future these gravity batteries, that's the way to go. Battery energy storages are taking off. They are being implemented in everywhere. So in Finland, I took the example so you can see the scales of those systems. There's, for example, in I think it's Ylikkälä, not Yllikkälä, power reserve. So this 30 megawatts in 2020. Lempäälä actually built last year a battery energy storage. So you can see it rather easily from Google Maps. So if you go to, there's Tampere and Lempäälä, and Hulikankulma is here. There's the Idea Park, and you can see the solar energy field. The other one is on the other side of the highway, and this, I guess, both are somewhat close to 2 megawatts of peak energy, or peak power rather. And the battery energy storage is in here. So that's the hole they are utilizing to cover the batteries. Olkiluoto has a battery storage. This Ylikkälä, this is the second one. So the first one is Power Reserve 1, and this is Power Reserve 2. So this should be a much larger one. And wind farm batteries are also being implemented. So that's from this Lempäälä system. A lot of batteries. And if you're thinking about the space usage, so as a whole, the footprint of the area required for this the largest system seems to be 1,000 square meters. So it's not just the battery itself, it needs the transformers and so forth on the area. So that's a part of this Lempäälä Lemene energy community. Related to heat storages, in Finland, this is going to be, I guess they are advertising it at least as the world's largest seasonal heat storage. So that's going to be some 90 gigawatt hours, close to 100 gigawatt hours. So that's really massive. So they have 3 tunnels, 300 meters long, and they will be constructed in a depth of approximately 100 meters. So that's going to be filled with hot water. And they can discharge the hot water from above the water column, and the colder one is going to be on the bottom. So hot water in there, temperature goes up to 140 degrees without boiling because it's going to pressurize itself with the hydrostatic pressure, and 90 gigawatt hours. So one charge of that to its full capacity, it's going to be 8 million euros. And the total cost of this system is going to be some 200 million. And there's some investment supports given to it. That's Kehä Kolme, so the highway in Helsinki. It's going to be built under it. Estimated to be finished in 2028. This was another kind of interesting idea, this kind of a heat pit. So you excavate ground and kind of build up the walls to the pit. And then you have some, I don't know what they use, and I don't know the word, pressuplastic, whatever, to kind of retain the water in there. And then you're going to put, this one doesn't have the cap on it, but you're going to put some 0.5 meters of this insulation above it. So it can go up to 80 degrees, and by the end of the winter, it has cooled up down to 40 degrees. So it can be used as a district heat system support, and 20 gigawatt hours. And this is kind of going to be the benchmark in a way to see how much it costs. So that's supposed to be rather cheap. It covers a lot of area, so the land usage is high. Discharging and charging power, some 30 megawatts. An estimated cost of 20 millions, so 1 million per gigawatt hour. So in that sense, if you're talking about the, this is a smaller system, but if you're talking about this Vantaa system, it was 90 gigawatt hours and 200 million. So that would be like twice the price. And then our students in, I don't know, was it 2016 or 17, they founded the Polar Night Energy, and they are making these sand batteries. So that's a really, it's a good idea to store thermal energy, for example, in sand, because when you're having these storages, it's kind of self-insulating if you heat it from the middle. So in that sense, this would be a really nice topic for even a PhD thesis, how to kind of manage the energy storage in a way that where to charge and where to discharge. And if you were to have, for example, this one to be used as power to heat to power, you can use, for example, Brighton cycles. And I found this was an idea in 2018, I guess. Let's see if I still have it in here. So there's a system that utilizes this, I'm guessing there was some kind of a circulating fluidized bed in here. So there's moving sand, and then you have these heat exchangers, and there's Brighton cycle, I guess. So gas steam turbines, but I'm thinking that this Brighton cycle could be utilized in it. There's a Finnish company called Aurelia Turbines that's utilizing, or rather constructing, these micro gas turbines. So that could be utilized in conjunction with this kind of a heat battery. But it requires going much above the temperature that this is operating. This is operating maybe up to 600 Celsius. So you would have to go higher to get an kind of reasonable efficiency for the Brighton cycle. But of course, there's the ability to, if you have the Brighton cycle, you can extract that excess heat out of there and make another one of these ones. So there's kind of CHP production in there. So Kankaan battery is going to be the first. Pornainen is the one that's being built at the moment. It's 15 meters in diameter and 13 meters high. So it's 10 times larger, 1 megawatt, or 100 megawatt hours, scaling up to, let's say, 10 megawatts and 1 gigawatt hour, 30 meters and 13 meters high. I asked Tommy about this. He's the other founder, and he said that there's no upper limit. It can be built up as large as the customer wants to, e.g., 100 gigawatt hours. So 100 gigawatt hours would require volume of 1 million cubic meters, so 50 meters, and a footprint of 136 times 136. So that's going to be rather big storage. And of course, in this, there's this self-discharge, but it's self-insulating in a sense that if you heat up the middle, there's going to be a lot of sand that kind of acts as an insulator in there. So large heating pipelines and connected, it has to be connected to the power grid because you're heating it with electricity. So basically you're heating, for example, air and blowing that air through in pipes through the sand battery. Optimal location is, for example, a decommissioned power plant site because there are the connections for the electricity and maybe even for the district heating systems. And this has the this has the capacity of producing really high temperature district heating system. And this is the kind of, in my opinion, the most interesting power to X to power project at the moment. In 2023, with Siemens, they made this in France, in a village that I'm not going to pronounce. They used the CHP system that ran on 100% hydrogen. So it's a 12 megawatt electrolyzer, solid oxide, produced hydrogen at a rate of 164 kilograms per hour. And then there was this gas turbine producing 10 megawatts of electricity using 100% of hydrogen. So this was the first kind of test that you were, you were using or utilizing this system in a way that you had electrolyzer, you had compressor storage, and then you had this CHP production via hydrogen gas turbine. And they were running it, I think, only for 4 hours with pure hydrogen, but that was due to the limitations on hydrogen production and storage rather than the technical limitations of the turbine itself, because hydrogen combustion is going to be really different compared to natural gas production. So in this sense, the charge and discharge have been completely detached. So you can store the hydrogen, you can run it through pipeline from point A to point B, and you don't need to kind of, it's based on the storage amount that how much capacity does it have. So it's really free to be charged and discharged. It's not kind of bound to too tightly in that temporal range or spatial range as, for example, a battery energy storage. So that's most likely going to be the system of the future, but we're going to have to wait for that for a while because the pipelines take a lot of time to build, and which one is going to come first, or the hydrogen production or hydrogen consumption? Of course, there's hydrogen consumption already. There has been a lot of hydrogen consumption in Finland in the oil refinery. They've been using it for hydro treating and hydro cracking, so it's for oil production.
There is efficiency, it's still not
Sorry?
There is efficiency, it's less efficient. What I heard for 30 to 40%.
Yeah. So it's the overall efficiency, it's not going to be that high, but remember that's for electricity production only. So in here, if you can utilize this heat recovery, then that's going to be the key to improve or boosting up the recovery, the efficiency rather. So if you have usage for heat, then it's going to be thumbs up. But it's going to make the system more complicated. That's sectoral integration in that sense. So sectoral integration to industry that's going to be utilizing hydrogen, and sectoral integration to industry or district heating or whatever that's going to be utilizing this recovered heat. Yeah, please.
They should have some limitation for their input of electricity or not. For example, in the case of it is a gigawatt scale, and is it possible to have a kilowatt scale also or not?
In electrolyzers, I think the overall, if you're talking about hydrogen production, it has to be high. And also, I mean, they are modular. They can be built modular. But the main restriction in here is that I think, contrary to the common belief that the electrolyzer can kind of follow the load and the electricity price, so you can switch it on and switch it off and switch it on and switch it off, that doesn't really apply. The electrolyzers at the moment are still so valuable, so they have so much capex that you have to produce the hydrogen pretty much year round. So you cannot really follow the electricity price that much. And the way I've been discussing with the people that are running with or testing with electrolyzers, there is a possibility that it can be kind of yanked on and off for a while. But in the long run, most likely that's going to be destroying the electrolyzer. So you have to run it throughout the year, and the running has to be a bit more smooth that was anticipated. But for your question, can it be a small system? If you're going to produce hydrogen, the economies of scale will start to take effect. And if you're making a really small system, then the kind of specific cost is going to be really high. So most likely these are going to be larger installation and with modular electrolyzers. A good example of this in Finland is this rain gas that's going to be built in Tampere, the rain gas plant. One of them will be built in Tampere in conjunction with Tammervoima, so the waste incineration. They're going to use the CO2 from the waste incinerator that's been, there's going to be a CCS plant or the CCU plant, carbon capture utilization, and they're going to make e-methane with that. So that's, I think, if somebody remembers what's the scale of that, I think it's 40 megawatt, the electrolyzer, but I might recall it wrong. So that's the at least the Finnish electricity storage and energy storage field at the moment. There are projects related to thermal energy storages. There are projects to electricity storages, which are related to more specifically the battery energy storages and this pumped hydro storage. So that's pretty much what's going on, and we have been borrowing Sweden's and Norway's the systems for quite a while, in a sense. So mathematical modeling of energy storages. First, you have to define the system characteristics. So before you make the mathematical model, you have to think about the characteristics of the system. So how much is the charge and discharge power? Are they separated? Are they kind of linked to one another? What's the energy capacity and so forth? But what's the discharge, or rather the round trip efficiency and so forth? So energy storage type, maximum, minimum charge, discharge rate, energy capacity efficiency, degradation rate, cycle life, operational constraints, and environmental factors. Can you operate it? Can you, for example, build a battery energy storage for your household outside or do you have to put it inside? Because if you have 100 kilowatt hour battery energy storage at your house or an apartment building, which they are offering now for lease, and you have it stored in the basement, if it starts burning, you know how difficult it is to put down an electric vehicle fire. Then I would definitely want to store it outside. But does temperature affect to the efficiency, for example, load variability, renewable generation data? So you have to start taking into account external factors. And for example, in here, you can see the discharge curve for battery, supercapacitor, and compressor. So supercapacitor, this is an area I know really little about, but allegedly this behaves in a way that the power decreases linearly over time. With batteries, you can extract, if you have this certain depth of discharge, you can get a really nice stable profile of power out of there. And for example, with gas, it starts to exponentially decrease when you decrease the pressure of the system. So those are the things that you have to take into account. You have to set up these state variables, so describing the system's current condition. So batteries, for example, state of charge. How much do you have the state of charge in the beginning? If you have a 10 kilowatt hour battery, if it's going to be 5 or 10 kilowatt hours in the beginning of the calculation. And then there's the state of health. So as an overall system, is it in a good condition? Is there been some degradation over time and so forth? Charge, discharge, power, and temperature. So they have to be stated in the beginning. So if you're thinking about the state of charge at the time, if you multiply that with capacity, then dt times pt is going to be the equivalent. And in here, if you think about state of charge, you can think about for example, water reservoir. With batteries, it's like easier. I can see from my phone that how many percentages of the battery capacity does it have. But for water reservoirs, you can check the maximum amount that you can store in there, and then there's seasonal variability. So that's been affecting to Finland's electricity price for a long while. And that's actually, if you were to make a serious model for what we made with the neural networks, kind of a serious business with trying to predict the electricity prices in Finland, you would have to take the Norwegian-Sweden reservoir into account. So you would feed that into the neural network. To some extent, that data is available on the internet, at least for a few years backwards from here. Then define energy storage dynamics. So how the energy is stored and retrieved based on system characteristics. For example, for a battery, there's going to be charge and discharge efficiency. The system might have different efficiency for charging and discharging, and it might be a function of the state of charge. And there's going to be degradation. So batteries degrade with the cycling. So when you do the cycles, it's going to start to degrade over time. And that's a matter of operational strategies. Are you going to use from 0 to 100? Because for phone, for example, you might not want to charge it all the way up to 100 and use it till 1% and do that again. You want to have a bit shallower this depth of discharge and charge. For pumped hydro, for example, you have the flow dynamics. So if you have this kind of a system, you have to take into account in the model that if you start releasing water from the upper reservoir, it's going to take some time. not maybe in this system since this is filled with water, but for example, if you have this run or the river system and you have some pondage in here, you have another plant in here. If you produce electricity here, there's going to be a wave. It's going to propagate through the river and it's going to take time. You have to take that into account in the model. So most what we are going to be doing here, we're going to be idealizing a lot of these systems. So then you have to incorporate external data and constraints. For example, if it's a power, it's connected to power grid, which pretty much all the systems that we are interested in are to some extent, because that's the renewable energy connection. Of course, it can be an off-grid system, as I'm going to show you, or what I showed you already on the first lecture and the second one. So that was an off-grid system with battery energy storage. So grid demand, renewable energy generation have to be taken into account, capacity limits, and then you move on to simulating the system behavior. So the models they are kind of sub-models that tell you what's happening in the battery, what's happening in the charge and the discharge. But then the simulation is something that you run the model through or over time. So once the state variable system dynamics have been defined, the simulation itself can begin. And for the simulation, you have to know, for example, these external data and constraints. So what's the load profile that has to be followed? Then related to this mathematical modeling, you might optimize the size of the system, and you might want to optimize the dispatch of the system. So when to charge and discharge. That's kind of like the optimization problem whenever you have a fixed system. This optimal sizing, how big of a battery do you have, can be done before that. But when you've decided that this is my battery, then the environment changes a bit, the electricity price changes a bit, the load or the demand rather changes a bit. Then you have to start talking about the optimal dispatch. And usually that's something that you can utilize a lot of different kind of algorithms, and there's no kind of easy way how to do that. That was an example on this Journal of Applied Thermal Engineering about this engine. So these are diesel generators, and they provide thermal energy for this organic Rankine cycle in here. And the idea was to dimension. So this is optimal sizing. How big of a thermal energy storage would you have to have in order to kind of stabilize the heat going to this ORC? So this ORC with a certain 12 megawatt thermal with 35 megawatt hours of thermal storage could kind of like, that's the available heat on the red, and the blue one that was stabilized with this thermal energy storage. So there's the thermal energy level, or the thermal storage energy level rather, with the dashed lines. So you can see it's running up and down. So there's an example of this dimensioning optimization. And what is sufficient? That is something that you have to decide as the modeler or operator. So the energy change is a function of time. So power in, power out. So how much discharge and charge has to be made. And it can be simultaneous. You can charge and discharge it at the same time. In my kind of models or these calculations, I separated them in a way that they don't happen simultaneously. But you can, for example, plug the phone in and start using it at the same time. So it's pretty much equivalent of that. And the effect of charging and discharging efficiencies. So you can have discharging efficiencies and charging efficiencies. So they have to be put into the equations. And what it means that, for example, this pumped hydro storage system, since you have a different system of charging it, there's this pump that's running the water upwards. So you need water pipes, pump, motor, transformer, and this can be a separate system than this discharge. So there's water pipes, turbine, generator, transformer, and so forth. So input electrical work, at first, it's going to meet Mr. Charging efficiency. And after that, it's going to meet Mr. Discharge efficiency. And what you're left with is 77.3% of the original electricity. And that is, of course, a rather good round trip efficiency. So that's the round trip efficiency, both of those together. Then the systems might face capacity fade due to these charge cycles or due to kind of aging. So, for example, in here, electric vehicle aging or electric vehicle battery aging. So low state of charge and high state of charge. So that kind of means the depth of the cycle in that case. So if your cycle is going to be rather shallow, or compared to one that's being really close to 0 and 100, then the degradation rate is going to be higher with more or less shallow operation. So you can take that into account with the initial capacity that you can utilize, and there's this term K, degradation rate per cycle, and that's something that usually has to be tested. That's really hard to kind of model. What they're trying to do is to use, for example, digital twins to kind of estimate these beforehand, but it's really hard to take everything into factor. And N is the number of full charge discharge cycles. And that's something as a modeler, if you have this kind of a rate or capacity and you're operating really on a shallow level in there, how do you calculate these cycles? Well, you can, for example, as in here, equivalent full cycles. But what is an equivalent full cycle? That's not self-evident in every case. Then the depth of discharge. So the rate of degradation depends on, as I said, how deep the batteries discharge. So the depth of discharge, shallow cycles or deep cycles. Deep cycles lead to fast degradation. So this F dot, it means that the more deep cycles you're going to be using, the faster degradation you are going to be facing. And that was shown in here. So how to simulate these systems? The simulation itself is rather straightforward. It doesn't require understanding like this mathematical solving method, like complex mathematical solving methods for these differential equations. It's usually just in Excel or in Python. You're just referring to the previous time step. And that's what we're going to be doing in the exercises. We're going to build a simple this energy storage system. But what kind of simulation techniques can you use to in here we're talking about, for example, battery arbitrage. So buy when it's cheap, sell when it's expensive. So that's what you can do with the batteries. That's called battery arbitrage. So the first thing that comes into mind is using thresholds for charging and discharging. So for example, you can set a charging threshold where the battery starts charging, and when the price is below a certain level, or when the price goes above rather certain level, then you start discharging and selling. So if there's your price, you set a limit. You can set two limits, but only one is sufficient. Above this, sell. Below this, buy. And similarly, you can set constraints for maximum and minimum charge levels. So to prevent this deep discharge or overcharging. It's really simple to implement, and it can be effective when battery behavior needs to be controlled in a predefined range. So in that sense, that's a good way. It's also a fast method compared to this full optimization. If you're going to go and optimize the system throughout, for example, a year to see kind of the cap, how much profits you could have made, then this might be the thing you start from. But it's not entirely optimal, as I'm going to show you. Then this rolling horizon, in my opinion, is a lot better system. So rolling horizon, it's kind of what is more comparable to reality. You have 24-hour window in which you're going to make the optimization. And then at that point, you're going to say, this isn't exactly the price point that you're interested. You're interested in whether you're going to charge or you're going to discharge. But you're going to make the optimization for 24 hours. For example, if you have a large battery capacity and you see that the price is going to be really level, like 18 hours, and then it's going to go upwards, then of course your optimization algorithm is going to say that let's charge now and save it for later. Or if it's going to go upwards a couple of steps, so it's going to be level, then it's going to be upwards and upwards. I'm going to draw this one into this whiteboard, so we'll see whiteboard. Man, a lot of windows there. So if your electricity price is going to go like this, so there's the price and there's the time. It's going to go like this. If your kind of field of view, the horizon is going to be this, then of course you're going to charge in here and immediately going to start discharging in here. But if your rolling horizon sees that, hey, there's even more kind of price to catch, you're going to charge here, you're going to charge here, and you're going to start discharging in here because it has the higher value of overall production. But in the rolling horizon, you make the optimization for 24 hours, and then you move on to the next horizon and the next. So the only time step that you're going to kind of select is the one in the beginning. So this is what you're essentially doing with this kind of a battery arbitrage. You're only going to see, well, it's not exactly 24 hours ahead because the spot prices are released around 2 o'clock for the next day. So in that sense, you're going to kind of catch up for the horizon, then it's going to move 24 hours again, then you're going to catch up to it and so forth. But in my calculation, I just used the rolling horizon of 24 hours. Reduces the complexity and computational cost by focusing only on a small, manageable time window. Accounts for uncertainty in long-term forecasts, providing more flexibility if you have a longer horizon. But the rolling window might miss long-term trends. So if, for example, in here, the electricity price would go still upwards. Then you started selling in here or selling in here, and then your battery was already empty when you would have made the most profits from here. So let's make a simulation. Let's have a battery of capacity of 20 kilowatt hours. These, if it's megawatt hours or kilowatt hours, now it doesn't matter. Then there's the discharge power of 1 kilowatt and charge power of 1 kilowatt. And this is for battery energy storage, this would be really low. So it would be much higher. I just wanted to emphasize that this would be much larger than the charge and discharge powers. For example, with pumped hydro, that is the case. Of course, then the capacity would be much larger. I took 2023 price. There's 1 month in there, and I gave it, actually optimized the threshold below which you buy, above which you sell. And then I used the rolling horizon method. And what I got out of it was the state of charge. So you cannot go above 20 kilowatt hours, and your charge and discharge rates, they can only fluctuate between 1 and -1. So discharge -1, charge 1. And what you pay for is the charge, and what you get out of it is the discharge. So those are the prices that you want to kind of match. And I tried 3 of these methods. So this sequential least squares programming, hard word to say. So that's kind of an optimization of the full span. And then the threshold system, and then I tried rolling horizon with this sequential least squares programming. So what it does, it optimizes the second version, the SLSQP. It optimizes the entire span, where the week, where the month, where the year. It was like, I know everything in advance, so this is probably going to be the best solution. But in this case, it was just slightly better. This was for 1 week. So this is for 1 week. And the threshold kind of, it came close. When I started optimizing 1 month, I noticed that this started failing. It didn't give me anything because the optimization window there were too many variables. It just said that, okay, I'm out. So it was a question between the threshold and rolling horizon optimization. And then when I simulated the entire year, this was the case. So this rolling horizon beat the threshold value. Well, not with a significant, well, it's a significant margin, but I would have expected a bit more. But either way, since you don't know in advance what are the prices going to be, then this rolling horizon is a really good optimization technique. I tried even this genetic algorithms that would know the entire year beforehand, but it kind of started choking because there's too many variables to change. So what you could do if you had more time, you could give this curve or the curve for the rolling horizon optimization, charge and discharge as an initial guess for the genetic algorithm and let it run its course after that. But what would that do to you? That would say that if I knew the future, then I would get this much money. But this is more realistic. And of course, you have to kind of test these models. So if I have the threshold in here, so the threshold is going to be 27 for both charge and discharge. So what it's going to give to me, let's see if it works. Yeah, that's for 1 week. So as you can see, I made a test case. My electricity price in here is 10, and in here it's going to be 40. So what the algorithm, because it optimizes everything in that time span, it knows everything before. In here, it starts or rather charging, so it costs money. So the battery energy level goes up to 20, it retains it, and it starts selling immediately as the price goes upwards. So charging, discharging. That's a reasonable thing to do. So let's try the rolling horizon version. So in here, it's pretty much the same, but the optimization algorithm kind of decided, rather than using this really fast and high discharge, it kind of made it in a smaller ramp. Or actually, this is the one that sees the entire week. Yeah, so this wasn't yet the whole rolling horizon, sorry. So this is the one that sees the entire week. And this one is the rolling horizon. So when I start this one, it gives me a bit funkier. So it only kind of realizes at that point that, hey, it's going to be a higher price. Let's start charging. So the previous algorithm kind of saw it already from here. It saw the future. But if I'm going to make the rolling horizon for entire year in here, so year, it's going to take a bit longer time. But as you can see, the time consumption here is manageable. If I were to start optimizing this with a genetic algorithm for the entire year, it would take a much longer time. So that is still manageable, and you can even affect to the horizon. You can put it smaller, you can put it higher, and you understand the higher your battery capacity is, the longer horizon you are going to need. There's no need for a long horizon if your capacity is compared to this power is going to be low. So let's see what it's going to cook for us. When I didn't have zoom on, it was a bit faster, but still, let's see what comes out of there. Yeah, so that's the charging and discharging. So I would have to zoom in here. So you would see charge, discharge, and that's the battery level. It pretty much never reaches the 20, and then there's the cumulative profits. So that would be battery arbitrage. That's one thing to use it for. That's not the only thing you have to use it for. And for example, you might have to set boundaries that at morning at 8, you have to have certain level of energy in the battery, regardless of the price. So when you're sizing the energy system, you need to know the energy demand and load profile. So peak demand, for example, energy requirements, so the total amount and so forth. Load shifting. If the storage system is going to be used for load shifting, ensure it can store enough energy during the load demand. So that's the capacity. How much capacity do you need? And for that, if you have, for example, an off-grid system, and you have wind power versus solar power, wind power needs a longer, or the fluctuation in there, as we saw in the first or second lecture, there were longer fluctuations. So with solar power, it's easy. It's like one day. Storage capacity, nominal capacity and depth of discharge has to be determined. And if you're thinking about the overall costs, in here, if you're increasing the energy system size, the overall costs are going to kind of start increasing rapidly. So initially, cost of storage unit is more expensive than additional unit later on, because later on the economies of scale start to affect. Impact of initial capital cost premium diminishes over time. So then it starts still going upwards, but not at that large rate. And the price of curtailment and dispatching of more expensive energy production assets decreases really rapidly in the beginning. But after a while, it starts to level off. And after a certain point, no matter how big of an energy system you have, it doesn't have any effect. Of course, this is not just the energy system size, it's also depending on the power. So the optimal system size would be maybe here. So you want to decrease the costs of dispatching those higher priced energy system or the energy assets. For example, the diesel generator in our example that I was showing to you, and most likely have time still to show to you. So optimal size means optimal power, discharge and charging ratios, or the values, and optimal capacity. So does that curve make sense to you? More or less? You're a tough crowd today. So in the beginning, if you have the energy system, it doesn't matter if it's 1 or 2 kilowatts. If you're going to set it up, you're going to have to set up a place for it. You're going to have a lot of wiring. You have to have, for example, some inverters and so forth. It's going to cost. But after you start adding additional capacity to it, that doesn't cost anymore as much. And in here, immediately, you're going to start seeing that we can reduce, of course, depending on the system. Again, we can start reducing the highest value energy asset. So you don't have to, for example, dispatch anymore the oil burner next to this fire station in here if you have a thermal energy storage. You can use the cheaper wood chip as a fuel in the bubbling fluid aspect, and so forth. But after a while, no matter how big of a thermal energy storage you get, it doesn't kind of fit to the system anymore. So power rating, discharge and charge ratio, that's something you have to, and power to energy ratio you have to consider. So how fast can you discharge it, and how big of a system can you make? You can see the abbreviations from this article in here. So FES was flywheel energy storage, and this was superconducting magnetic energy storage. CAES is compressed air energy storage. PHS is pumped hydro storage, and this is vanadium redox flow battery. So I'm not an expert in that flow battery in any sense. I think the difference is compared to lithium ion batteries. Hopefully I'm not butchering this. If somebody is from the electrical engineering side, just please call me out. But I think in this redox, so reduction oxidation, redox flow batteries, the energy is stored in the moving electrolyte itself. And for example, lithium ion batteries, it's stored in the electrodes. So in that case, if you have more electrolyte in there, you can scale it up more easily. So that's why the flow battery, it can be a higher capacity than, for example, lithium ion batteries. So power quality, bridging power, and energy management. By the way, the all subcategories of these kind of energy management, well, these are energy management in a way in here, but the all subcategories related to these, you can read it from this article. This was a really, really good article. Let's see if I can actually open it from here. We still have some time, so it's this one. Hopefully I can open the DOI from here. Yeah, So yeah, in here you can see, by the way, the pumped hydro and lithium-ion batteries comparison, how much the capacity is. Well, that was I don't know if it was a few years back, but still. In here, the category, power quality and regulation, bridging power, energy management. For example, here, load following, wind power smoothing, spinning contingency reserves, and ramping from 1 minute to an hour. And then you start to go to this peak shaving, and in here, transmission curtailment, energy arbitrage, because it operates in the electrical markets. It needs 5 to 12 hours capacity, and it has to be, well, it doesn't have to be that large for energy arbitrage, but to get a system that's usually operated, it has to be really large. And then you start affecting in here seasonal storage and annual smoothing. And that's the one they want to do with the, for example, the pit that I was showing you related to the heat storage. So this was a really good article, and you can see a lot of these power range, energy density, power density for all of these different kinds of systems. So in that sense, if you want to, and for example, charge and discharge time, response time. So whenever you need some references for those, this is the place to go. It has a lot of these references, and you can see a lot of really specific values. So let's go back into here. Round trip efficiency. So round trip efficiency, if you see in here, and then there's the storage duration. In here, there's interestingly hydrogen and combined cycle gas turbine and methane combined cycle gas turbine. I guess I'm not sure, but I would think about the methane being lower in here was that it's produced from hydrogen then. But round trip efficiency, lithium-ion battery and flywheel, they are the keys in this. So lithium-ion battery it's a really good technology for electric vehicles, especially because the efficiency is so damn high. GAES, as you saw from the previous ones, this would maybe represent adiabatic GAES, where you kind of store the heat produced from the compression. But then it's not nearly as high, for example, in this German Hundorf or the GAES. That was something around 42. So that depends or the affects your sizing. Then charging and discharging cycles, cycle life, cycle depth. What's the technology going to be and what these are going to be in relation to that. Operational constraints. If you have some temperature ranges that you have to have, so for example, you cannot heat up the battery after or above certain points. Actually, there was a master's thesis done related to these battery cooling systems by optimizing this water flow in a certain cooling duct done with computational fluid dynamics. So that's something that was done for our department. Safety regulations. So, for example, can you place the battery inside your apartment building, or do you have to place it outside for fire safety? Cost considerations. Capital cost. Remember, whenever you have a high capital cost, then the system has to have high operating hours. Otherwise, it's not sufficient. Or then you have a market gap. You've discovered a market gap that nobody else has discovered. But in these systems, they are highly kind of competitive. So if you want a system with high capex, then you have to have high operating hours. Grid connection and integration. So what kind of a system do you have to install if you want to connect it to the grid? And most of these systems are connected to them. But we watched this simulation as a storage simulation as a part of energy system with this NATO energy system. So there was the consumption, there was the conversion, and then you could use storage, or you could use direct direct usage of these solar and wind. And how big of a storage do you have to have in order to decrease the use of these dispatchable diesel generators? So in that sense, this is a really nice system in a way that it doesn't have the interaction with the electricity grid. So everything that happens within the system. So you would have to define the load for it. Then you would have to define how much energy is being produced from these sources. And we're going to be looking at in the next lecture in a bit more detailed manner. And then the storage. So how big of a storage do you have to have, and how big, for example, discharge and charging rates do you want it to have? So that's something that we're going to be doing in the calculation exercises to some extent at least. So I'm going to give you some consumption. So that's the load profile. And then there's the production of solar and wind. And after that, you're going to have to define how big of a battery you would have to get in order to kind of cope with this kind of a load profile. So you have the production, or excess production, for example, in here, and then you have the deficiency in here. So in here, you would have to dispatch the battery energy system. So this can be done, for example, in Excel. And as you can see, when I'm calculating the energy storage in here, I'm always referring to the previous time step. So that is the initial state of my system, and I'm just solving it step by step, moving forwards. In here, there's no kind of, well, there is some dynamic interaction between this energy production and or rather consumption and battery. But when you're starting to incorporate this battery as part of the electrical grid, then it's going to start affecting at some point to the dispatch order, to the merit order. Because if you have a large enough battery, if you can provide large enough capacity, and it's going to be cheap for you to utilize it, then it's going to start pushing some other more expensive system out of the market. But in here, there's no such dynamic. So the wind is going to blow and the sun is going to shine. They are fixed in here. And what we're after is how much the diesel generators have to be dispatched in there. So I'm not sure if we're going to make the economic calculation, but whenever you are trying to make this optimal sizing of the system for the system, you can make it in a way that you dimension the battery in a way that it covers everything, and that's the point where I'm going to cut. Or maybe it covers 90%, and that's the point where I'm going to cut. But whenever you start taking into account the economic realities, so the higher the battery system size, the higher the cost is going to be. So the function, as I showed you, it's going to be something like this. In here, it was rather linear behavior because this is a really simplified system. And I don't take, for example, into consideration that if the battery size increases, there's no economies of scale into play. But you can see that if I put a small battery, smaller initial charge, and smaller charge or discharge, this was the idea to see that how much of this curtailment do we have? So how much of the energy from the solar and wind production do we lose? Because we cannot use it anywhere. So that's being curtailed. And then how much of the energy usage has to be covered with the dispatchable energy sources. So that would be the diesel generators. So at least this is something what we are going to be covering in the calculation exercises. tomorrow and on Friday. Yeah, so that was about the energy storage system. So as I said, there's going to be many aspects you can go or kind of dig from this subject, but I tried to select the most relevant related to understanding these different scales. So you want to know how big systems there are, what are the current systems being used, what are being built, how much energy, and how you can calculate it, for example, from the renewable energy, and what else? The mathematical simulation. That's rather straightforward. The optimization is the harder part. Okay, let's stop for that for today, and I'll be seeing you on the calculation exercises then.